Hello, my name is Shree, and on behalf of my collaborators at the Cornell University, I would like to present our paper on exploiting natural language for efficient risk-aware multi-robot search and rescue planning. This work is motivated by the high-level idea of inducing cooperation in human-robot teams. Trained humans, like firefighters, possess domain knowledge for decision-making, but we cannot expose them to severely unsafe environments. On the other hand, robots are relatively easy to replace and can capture scene characteristics through their sensors. An obvious application of our work is search and rescue mission, where we want to ensure safety of the critical agents like humans while being able to rescue the victim. Based on our interviews, we found that firefighters usually communicate verbally during missions. On the other hand, our robot is equipped with visual sensors. So, the key challenge here is to make sense of the multimodal data coming from multiple sources and accordingly generate a plan to rescue the victim while ensuring the safety of the human agents. We ground the problem statement to leveraging the capabilities of the human and camera-equipped robot in order to safely rescue a victim from an unsafe environment. We propose a pipeline in which the commander-in-chief of the mission provides descriptions that corresponds to certain danger levels. These descriptions are processed by a machine learning model to find similarity with the current scene. This is followed by a probabilistic inference of the danger level belief. Finally, the belief is sent to the planner that generates the rescue plan with accounting for danger in each of the explored regions. Now, we will go through each of the segments in more detail. Let us start with the scene danger assessment model. The picture shown here is, let's say, the floor plan of the area where we are going to carry out the mission. First, we look at the big picture and then divide the world into smaller regions, abstracting it as a graph. Each node in the graph consists of local collection of sensor data like images. We assume a discrete danger level scale with 1 denoting low danger and 5 denoting high danger. The goal is to assess danger level of each image at a node and then combine them together to assess the overall danger level of that node. Since human is providing natural language descriptions, so combining that with the images and estimating the danger level becomes a multimodal inference problem. Let us consider an example where the human provides 2 descriptions with their associated danger levels. The machine learning model takes them as input and finds similarity score for each image sentence pair. We convert the similarity scores into one hot vector by using an appropriate threshold. This is to reduce the effect of noise. Since there is high match with the first sentence, so the corresponding danger level that we get is also high. Now the next question for us was, what type of machine learning models can we use to achieve the task in hand? Fortunately, since 2018, some authors have proposed visual-lingual models which are suitable for various tasks involving language and image data. However, the key challenge is the lack of dataset that can aptly represent unsafe spaces. Since it is hard to replicate the unsafe environments, instead, we found a synthetic dataset called DISC, which consists of images from post-disaster scenarios. However, it only consists of images and the descriptions are missing. We started by sampling 1,000 images from the dataset and conducted a survey on Amazon Mechanical Turk to get 4 labels for each image. A typical response consists of 2 sentences. For example, for the image shown here, one of the participants wrote, "The office is severely damaged and there is debris everywhere." The second sentence says, "The office furniture is damaged and thrown all over the office." The dataset is used for training and testing performance of the machine learning model. Our dataset is available freely in the link shown below. To compare the different state-of-the-art visual-lingual models, we evaluate their ability to find the correct image given its description. This is achieved by first finding the similarity scores between all the gallery images and the description. This is followed by arranging them in descending order of the scores, that is, the most likely image to the least likely one. Finally, we evaluate the rank performance, which is defined as the accuracy of the top K hypothesis from the model. Here are the results. One of the clear observations from the table is that the model fine-tuned on the disk L dataset outperforms the pre-trained model. This means that fine-tuning it on our dataset helps it to learn certain key characteristics of scene which are unsafe. In addition, we can see that Wilbert, which is a more recent model, outperforms CAN. Thus, we decided to use Wilbert for most of our work. Once we have the model that finds a similarity score between the image text pair, the next task is to combine the scores from multiple images at a node to assess the overall danger level. For this task, we first convert the similarity scores into one-hot vectors based on an appropriate threshold. Then we count the frequency of ones across images and then normalize it over the total sum to get a probability distribution of danger. For this given example, the danger level distribution looks like this. To evaluate the danger estimation performance, we compare it against human ground truth for the school environment in the disk dataset. The node danger map as per the human is shown in the top figure, and the maximum likely danger estimate from the robot is shown in the bottom figure. As we can see that the estimated danger matches closely the human ground truth. For a detailed quantitative analysis, please read our paper. Now Beatrice will explain the planning aspect.
Hello, this is Beatrice. So for the multi-agent planning, we want to reason over the big picture, much like humans do. So we abstract the low-level details, such as local planning, navigation, and controls, and we formalize our search problem as a combinatorial optimization problem. Here on the right, you can see a simple search scenario where probabilities P represent the belief of target location. We want to find our target, but we don't know exactly where it is. Such problem was dubbed by Hollinger as the multi-robot efficient search path planning. And the key question here is, how should the searchers move to maximize the chance of finding the target? We proposed in a previous paper to apply a mixed integer linear programming as a planning paradigm for this problem. It turns out MESPP is fast and scalable while dealing with probabilistic search. It provides centralized and distribution solutions for NP-hard problem and presents almost 99% decrease in runtime compared to the current state of the art. So we developed a model and we input the target belief, the sensors model, the agent positions, and the MIG model give us the planned path. In search missions, we want to address the notion of danger. So we introduce our online, risk-aware, multi-robot efficient search path planning by associating to each vertex a probability of loss given danger. So now the planner weights in the danger and the target capture probabilities through added constraints for a conditional planning with human help. In this context, we have a shared perception and autonomous planning. So as Vikram explained before, the commander-in-chief can tell the robot that a room engulfed in flames equals extreme danger, And then the robot can go around exploring the environment and identifying which scenes correspond to that description. It is then able to come up with a scene danger distribution, which, together with the danger thresholds from each agent, is fed into the MILP models, which returns a planned path for each agent in a decentralized manner. And it turns out that customized danger thresholds allow protection of valuable agents, for example, humans. We evaluated our proposed approach through numerical simulations, varying the configurations of the planner, the a priori danger knowledge, and the team makeup. Our results suggest that when compared with a regular planner, a risk-aware planner does have a slightly decreasing performance, measured by a decrease in success rate and slightly increase in mission time. However, the capture time of the target is similar, and there is a significant increase in safety, which means we were able to reduce agent loss and allow protection of specific agents. So the decreasing performance actually caused by the robots playing it safe and not exploring the environment as much. So clearly, it's a trade off between team performance and safety. We also evaluated our proposed approach through qualitative ROS gazebo simulations, which provides additional challenges. Here, we are dealing with the dynamics of the agents and their localization and navigation throughout a 3D environment. Recall our planner abstract low-level details, so it sees time and space as discrete, while in reality, they are continuous. So we are constantly going back and forth between those two representations. And the same happens with the agent's motion. While in the planner, we consider the agents to be synchronous, which means they move at the same time. Besides those challenges, our experiment showed that a risk-aware planner can reduce losses on one set of agents without significant loss in performance, even under practical navigation challenges and imperfect scene knowledge, showing that we can successfully leverage the human knowledge and the robot's capabilities for a safer yet efficient semi-autonomous mission. We would like to thank NSF for the funding, our lab, the Autonomous Systems Lab, and Cornell University. Here is our contact if you want to reach out. And a big thanks especially to Assistant Chief Tom and Chief George, who helped us gain valuable insights about real-world search and rescue missions. Thank you.